Good morning, everybody. Sorry for being a little tardy this morning. We will jump back into chapter 8 here. So we started talking about alcohols and ethers, and whatever we finish today is going to be fair game for the exam. So just a reminder there. I haven't got the exam made yet completely, but again, it's going to be similar to what you saw last time. Let's see. So where did we get to? We got through interesting alcohols, right? And we got to talking a little bit about ethers. Talked there, I think. Mentioned that. I think we got through that. All right, I think this is about where we're at. Does that ring a bell? All right. So, alcohols are bases. They're also acids. So they have both properties. So if we look at a typical alcohol, why can I say that they're going to function as both an acid and a base? That's right. So they can donate a proton, right? Because they got the OH, right? As far as organic molecules go, this is actually quite acidic. Alcohols have a pKa of around 16-ish. So very similar to water, right? And of course, the oxygen atom of an alcohol has lone pairs of electrons. And so they can donate those electrons to a variety of things. And so they can function as both acids and bases. And so a lot of times what you find these things working as is as bases or nucleophiles. And so what you'll have in a number of reactions is an alcohol will react with a strong acid. Give me some examples of strong acids. Hydrochloric acid.
Nitric acid.
Nitric acid. Sulfuric acid. HBr, HI, right? Those are the common ones that you all know of. They all have pKa's that are negative, right? So they completely dissociate when placed in water, right? And so if I take an alcohol, which is like water, and I place a strong acid in it, I would expect it to dissociate more or less the same as it would in water. And so you end up protonating the alcohol, and we call this an oxonium ion. Oxo from oxygen, onium meaning plus, okay? Oxonium ion. And so you'll see this quite a bit in some of these reactions with alcohols. The first step will be the protonation of the alcohol, okay? And then that protonated alcohol can actually function as a pretty good leaving group. Hydroxide is a poor leaving group because it's a very strong base. But water can actually be a pretty good leaving group. And so you can imagine having another proton here, this being positively charged, right? And let's make this like this so it's a little more plausible. But you can imagine this leaving now as water. Water's a good leaving group, okay? And so what you'll find is that protonated alcohols are kind of an intermediate in the step of some of these reactions. So for example, you can take a nucleophile, you can react it with a protonated alcohol, and you can do an SN2 type reaction with that. What's the problem there though in that reaction?
SN2?
It is an SN2 reaction, but what's the potential problem? Nucleophiles are also what?
Bases.
Bases. You could get elimination. That's a potential problem. What else is a potential problem? This is an acid, right? So nucleophiles could react as bases and just pull this off and you have a reversibility, okay? But under certain conditions, this actually works fairly well. So for example, you can take a primary alcohol and you can react it with HCl, and you can make, although the reaction is slow, you can make the alkyl halide plus water. Chloride is the nucleophile. It will displace the water as a leaving group at some point. It goes through this protonated intermediate. Okay? So, converting alcohols into alkyl halides, what we just talked about here a little bit. Right? There's several ways to do this. Okay? You need to know all of these ways. I can react an alcohol with HX, HCl, HBr, and HI. And I can make alkyl halides. I can react an alcohol with phosphorus halides, PX3. So it could be PBr3, PCl3, PI3. Those work. Or with a molecule called thionyl chloride, SOCl2. All of these reagents will react with alcohols to make alkyl halides. Okay? So, you can take let's take an alcohol. What would the product be? The reagent is a phosphorus halide, right? So what's the product going to be?
Alkyl halide.
What alkyl halide?
Sorry, can you say it again?
What alkyl halide? What halide?
Bromo.
Bromo, right? So that's going to convert that into an alkyl bromide, right? If I used PCl3, I would get an alkyl chloride. If I reacted that with thionyl chloride, what will I get?
Also alkyl chloride.
Also an alkyl chloride. You might be asking yourself, why do you need so many reagents to do the same thing? Okay, it turns out these reagents have different reactivities that we're not going to get to in this class, and there's reasons for using them. But what I can tell you is this guy right here is nasty as all get out. I've tried to do that reaction several times. I can get it to work, but if you let it warm up, it explodes on you. Not explode, but I mean, it heats up and it just boils out of the flask, creates a big mess. Thionyl chloride, not so much. So I can do that kind of chemistry pretty readily, okay? So, here's a few examples. Spend some time working with your partner, your neighbor. Come up with what you think the products of these reactions are going to be. We haven't talked about all of the reagents that are listed up there, and we're going to talk about them as we go through. I want you to take a stab at them. This rag has definitely seen better days.
Oh, yeah, I didn't remember doing it.
Pretty nasty.
So what, okay, so what's your process? Well, that doesn't help us, does it? Well, if you look at that, what you just wrote, I would say that B off goes there. Well, CL goes to that one. The other one, the same thing applies to the other one as well. Does that make sense? How was your weekend, sir?
Peachy.
Well, there's different varieties of peachy.
Sweet peachy.
Yeah. I put it all night of Thursday night, try to get things done. Things.
Mm.
From 8 PM to 3 PM we worked on it.
Why do we have a skeleton in the corner?
Crime scene dog. I have a habit of forgetting things I really need for class, so I just brought it with me.
You did?
Yeah.
That's yours?
Yes.
Okay.
Do you have that down?
Oh, yeah, that's true.
And they have.
So what do you think about the first one? What's going to be the product? What's the halogen in the reagents?
Bromide.
Bromine, right? Yeah, bromide. So you're going to make an alkyl bromide, right? So let's work through the mechanism. And let's just say we're going to use dry HBr gas. Right, so HBr. What's going to be the first step of that reaction?
Replace the OH with BR.
No, that's not going to be the first step. That's going to be the ultimate thing that happens. But what's going to be the first mechanistic step?
Is it SM1 or SM2?
You tell me. But let's work through the steps.
Is it the
The leaving group has to leave and the hydrogen one has to break off the proton.
Do I have a leaving group yet?
No.
OH is
Not
the,
yet.
yeah. Maybe the oxygen attacks the hydrogen in HBr.
Okay. One thing that you all need to remember, all organic chemistry, for all practical purposes, is nothing more than a series of acid-base reactions to get to the products, right? This is why acid-base chemistry is so important. This is a base, this is an acid. Do the acid-base chemistry, right? So, that becomes positively charged. Remember our formal charges, right? Plus bromide. Now let's get to Selena's question. Is it going to be SN2 or SN1? If it's SN1, the leaving group has to leave first.
Yeah, so it's.
What kind of carbocation would that make?
Everyone can
Primary.
have that.
That's right.
SM2.
So it's going to be SN2, right? So how do I draw the next step then?
The water leaves.
If the water leaves, I get a carbocation.
Oh,
The BR attacks.
BR attacks.
And simultaneously that
Oh.
leaves.
Yep. That's what happens. Now it says, or we can use sodium bromide and sulfuric acid and reflux. What does reflux mean?
Yeah, I can figure that one.
What does reflux mean? Have y'all heated up anything in lab yet?
Yeah,
With a little reflux condenser on top of it, and it boils, and it,
No.
haven't done that yet? That's what reflux is. Reflux means, it's like acid reflux, right? You have stuff come up from your stomach into your throat, but you don't actually expel it, right? It goes back down. That's why they call it acid reflux. To reflux something means to bring it to a boil, but you don't boil the solvent out. You have a condenser that condenses and it drips back down in. Okay, so that's what reflux is. So it turns out that if you take sodium bromide and sulfuric acid, you actually generate HBr. I can take a vial of sodium bromide salt, I can take a vial of sulfuric acid, and when I mix them together, it will generate dry HBr gas. That's how we generate it in the lab when we use it. So you can actually just mix all those together. okay? And so basically it's another way to generate HBr. What about the second reaction? Has everybody got what they need?
Would it be the same thing but with chloride?
Yep. So we're one carbon shy, right? We're one, yeah, propyl alcohol. And we're going to use HCl and zinc chloride. Okay, and we're going to get, what's the zinc chloride for? Wouldn't just HCl work here?
Is it just like a catalyst?
It's not exactly a catalyst because it doesn't get regenerated, but it promotes the reaction somehow. What do we know about chloride? Right, if I think about this, I get right? And then the SN2 reaction should happen. What do we know about chloride? Is it a better or worse nucleophile than bromide?
Worse.
It's worse. It's really not a very good nucleophile. Chloride will work, but if you did this reaction without the zinc chloride, it would work. It'll take a long time. So you add some zinc chloride to it, it speeds it up. And that turns out the mixture of HCl and zinc chloride is called Lucas reagent. It just speeds the reaction up. So it sounds kind of like a catalyst, but it's actually, you have to use a full equivalent of zinc chloride. You can't just use a little bit. Okay, so we don't really consider that to be catalytic. And so this is also an SN2 reaction because it's a primary alcohol. The third reaction right? So the product is going to be this water, as you might expect, but the mechanism is going to be what?
Carbon cation.
Yeah, this is going to be an SN1 reaction. Okay, this one is going to be SN1. Okay, it's exactly the opposite of the demonstration I showed you. Right. In the demonstration, you took T-butyl chloride and water and you got the alcohol. This way, you're going the opposite way, right? So what happens in the first step? We protonate the alcohol. Right, that's attached to a carbon that has 3 other carbons attached to it, so it's tertiary, right? It leaves. You get the tertiary carbocation plus water. And then the chloride from the HCl comes in and attacks and makes the final product. Right?
Why is it OH2?
Here?
Yeah.
Because it gets protonated, right? I just didn't show the step. So that's how you get that, and then you get the chloride coming in. Okay. So let's see if we're right. Yeah, butyl bromide, propyl chloride, and tert-butyl chloride are the products of these reactions. 2 occur by SN2 reactions, 1 occurs by an SN1 reaction.
So I was right.
You were right in the final step, yes, just not the first step of the mechanism. Yeah.
Wait, Joey, did you just flip around that carbocation when you got the last, the end result?
What do you mean flip around?
Because the way we drew it, the up one was already there.
Okay, so carbocations are flat and planar
Yeah.
because they're sp2 hybridized. But now it's sp3 hybridized, so it's tetrahedral. Yeah, yep, that's right. Okay. So we can take an alcohol and we can make alkyl halides from it, right? So if I take an alcohol and I react it with PBr3, I'm going to get an alkyl bromide. If I take an alcohol and I react it with HBr, I'm going to get an alkyl bromide. If I take an alcohol and I react it with HI, I'm going to get an alkyl iodide. Okay, we can make all of these alkyl halides from alcohols pretty easily, okay? But we can also make alkenes from alcohols by a process called dehydration. So I can take an alcohol, let's see, let's take one like this, and I can remove water, and I'm going to draw it like this for right now. So water can leave, and I can get at least one alkene out of it, right? In this case, since I have two beta positions, I can theoretically get two alkenes, okay? So the question is, how do you eliminate the water, right? I go to the bar, I order a drink, it's got alcohol in it, it just does not spontaneously decompose into an alkene. I've got rubbing alcohol at home, it does not spontaneously decompose into an alkene. It just doesn't spontaneously spit out water like I've drawn it there. It undergoes a beta elimination reaction, and you have to use what I call a dehydrating acid for this to happen. Sulfuric acid or phosphoric acid are usually what we typically use, okay? And so primary alcohols will do this, but you gotta heat them up. Secondary alcohols will do this at much lower temperature, and tertiary alcohols do this like a shot. I mean, you don't have to have it, actually it'll occur below room temperature pretty easily, okay? So primary, secondary, and tertiary alcohols can all undergo this elimination, okay? But it depends on the reaction conditions as to what you're going to, for the type of alcohol, you gotta be able to match that up. So, we learned in a previous chapter, right, that we can take an alkene and add water across the double bond. That was an addition reaction, right? What did we use for that? How did we add water across the double bond? We used some sulfuric acid, I heard somebody say that, and what?
Water.
Water. And we used a lot of water. In this reaction, are we going to add water? No, because these reactions are reversible, right? So, a dehydrating acid is typically a fairly concentrated acid, okay? It doesn't have to be perfectly concentrated, but it needs to be a little more concentrated than you might think. So if I took this alcohol and I placed it into sulfuric acid, I would get, as the major product, this alcohol plus water would be the byproduct. I am removing water from the alcohol. If you want to see dehydration in action, there are YouTube videos out there you can look at. I can't do it in here because it actually makes a smoky thing and would smoke everybody out. But you can take a sugar cube and you can take sulfuric acid and you can place on that sugar cube and you will see it start to steam. That's all the water that's leaving, and it will turn black and it will start to grow like a snake. It becomes pure carbon. It's a dehydration reaction because sugars have lots of OHs. They're really just alcohols, okay? And so you're making a bunch of you're removing all the water from the sugar to make carbon, basically, through this dehydration reaction. So what do you think the first step's going to be?
The H2 attacks the OH, or the H just,
Okay. What is sulfuric acid? Strong or weak?
Strong.
Strong acid, right? So it should dissociate.
Yeah.
The way that I like to think of sulfuric acid is as H plus HSO4 minus. Makes life easier when you think of it that way. Now what's going to happen?
Maybe the OH attacks the lone H plus.
Okay. So I've got a base, right? I've got an acid. So I can do that. Now what's going to happen? Okay?
maybe.
So if we do that, got a good leaving group. It's a secondary alcohol or secondary carbocation, right? What can happen? Is it going to rearrange to a more stable carbocation? Can't. I mean, it can rearrange, but all it's going to give you is another secondary,
Yeah,
right?
like you can't get a better one.
Can't get a better one, so okay, let's just leave it alone. Now what has to happen?
The HSO4 minus will attack the hydrogen.
We'll attack a hydrogen. Okay, so I've got hydrogens here on the beta carbons, right? So this is alpha, right? So everything attached to it. So which beta carbon is going to lose the hydrogen?
The one that have less hydrogen will lose the hydrogen.
Whose rule is that?
Like
Zaitsev's rule, right? And so, right, so now the base comes in, eliminates, you get the product, right, plus water, and it's catalytic in sulfuric acid. These are called catalytic dehydrate. These are catalytic amounts of acid that you actually need to generate these products, okay? There are two acids that work really well for this, sulfuric acid and phosphoric acid. Okay? Notice what didn't happen. HSO4 minus didn't attack the carbocation to make a oxygen carbon bond because these anions are very stable. They're not nucleophile. They don't behave as a nucleophile. Okay? They don't behave as a nucleophile. Notice I didn't say HCl or HBr because chloride and bromide are good nucleophiles and they can attack the carbocation. So you've got to have the right acids present for this to occur. Okay? Why is it that a primary alcohol has to be heated to higher temperature than a secondary alcohol?
carbocation is not stable.
It's not stable. So am I going to go through a carbocation intermediate?
No.
No. The primary alcohols always go through an E2 elimination process. Secondary and tertiary alcohols can undergo E1 elimination, right? And so they go through these carbocations that are much more stable. They don't require as much heat. But primary alcohols, you kind of got to heat them up quite a bit, okay? So, and it is quite a bit. So if you take some examples from your book, right? This is ethanol. This is grain alcohol. They put it in what appears to be pure sulfuric acid, and they heat it to 180 degrees to get this elimination to occur to get ethylene or ethene. Okay? This is an industrially important material. You all have probably heard of polyethylene, things like plastics. This is one way you can make ethylene from renewable sources. So you can take your corn stalks, you can make alcohol out of them, you can heat it up with sulfuric acid at a really high temperature and you can get ethylene. That's a primary alcohol. If you look at cyclohexanol and you mix it with sulfuric acid, you only have to heat it to about 140 degrees for this reaction to occur, okay? And so you end up generating cyclohexene at about 140 degrees. Tert-butyl alcohol, they say 50 degrees here. This reaction actually occurs at much lower than that in reality, and you get this alkene out of the product. So primary, secondary, tertiary, you can see that the temperature requirements go down quite a bit for these eliminations to occur. Okay? And we call them dehydrations because really what we're removing from the alcohol is water, right? And so that's where we get the term dehydration. All right. So let's come up with some mechanistic explanations. I want you all to work on a mechanism for the following dehydration. And remember, the little triangle means heat, so I'm heating it up a little bit. What do you think the product's gonna be?
It's gonna be rearranged. Because carbocation.
Maybe.
What we're trying to do is trying to,
Work the mechanism through to final product. Tell me what the final product's gonna be, but you can't figure it out if you don't go through the mechanism. What's the first step gonna be?
you have to break it down,
You have to break it down. What does that mean?
then you have to get the product that's on that line, right, you have to break it down to get it to over there.
So think of this as H plus and HSO4 minus,
Correct.
okay? Not bad. Every time you see an alcohol and a strong acid, the first step is always protonating the alcohol to make the oxonium ion. That is always the first step. I've got a Lewis base, I've got a Lewis acid, do the reaction.
That simple?
It's not, we're not done.
Oh.
Now what happens?
The OH leaves.
The OH can leave. And why can it do this?
It's a good living group.
I got a good leaving group,
And
and it's on secondary carbon, right? So we know we can go through a carbocation. Now what happens?
rearrangement.
What's gonna rearrange? True.
So we're gonna get a.
But what's gonna move to make the rearrangement
The
occur?
methyl group right next to it.
Right, so I've got some methyl groups that can move. And if I move one of those, I end up with what kind of carbocation?
Tertiary.
Tertiary. If I moved one of these hydrogens over here, what kind of carbocation would I end up with?
Still secondary.
Secondary, so that's no good, right?
Yeah.
So we're gonna migrate one of the methyl groups through a rearrangement, right? I now have a tertiary carbocation, whereas this one was secondary. Now what happens?
Draw the hydrogens on the beta carbons.
Okay, so I've got a hydrogen there, and I've got some hydrogens there, right? So what happens?
The hydrogen bond breaks and we get a double bond on in between the two methyl groups.
That's right, following whose rule?
So that.
Zeit says rule, right? It says that I want to remove that hydrogen. So I end up getting my sulfuric acid back. And I end up with that alkene. Okay? When you're dealing with secondary alcohols and tertiary alcohols, rearrangements are a real possibility. You're going to have to pay attention to them. Primary alcohols, that can only occur by an E2 elimination. No rearrangements are going to occur. Okay? So keep that in mind as you think about these types of problems. Okay? So far, what have we learned? We've learned that we can take alcohols and we can convert them to alkyl halides. We've learned that we can take alcohols and we can convert them to alkenes. But there's some other things that we can do with alcohols. We can do some things that your body actually does with alcohols. You know, your body doesn't take an alcohol and heat it to 180 degrees Celsius and eliminate something. Your body does not take an alcohol and react it with PBr3 and make a bromide. That doesn't happen. It's not those are not biologically relevant reactions. But your liver does take alcohol that you drink and convert it into other things. It will oxidize that alcohol. Your liver is an oxidation machine, okay? And so we can actually take an alcohol and oxidize it to other useful functional groups as well, okay? But before we get into that, you need to learn how to calculate an oxidation state. Okay? What did you all learn in Gen Chem about oxidation states? What does it mean to oxidize something?
Like, I don't know.
We technically can add oxygen. That is one way to oxidize. But there's a more fundamental definition of oxidation.
An increase in oxidation number.
True, but that's a result of what I'm talking about. Did y'all learn the acronym oil rig, where Leo the line goes Gurren? You learned that one?
Yeah.
All right, so what was oxidation? A molecule can either gain electrons or it can lose electrons, right? So what is oxidation? Losing electrons. And I always like oil rig. I'm from Oklahoma. Oil rigs are better than Leo the line, okay? So oil rig, oxidation is loss, reduction is gain. Okay, when we're talking about these things. And so you have to learn how to calculate the oxidation state of an organic molecule. And it's not hard to do. It's very similar to calculating formal charge, except we change one of the rules. Remember when we calculated formal charge, what did we do? We drew a circle, and we assumed equal sharing of the electrons. In oxidation states, we do not assume equal sharing of electrons, okay? So it's very similar to the calculation of formal charge, except we don't assume the equal sharing of electrons. So it's going to be valence electrons minus signed electrons is going to equal the oxidation state. That's the same as in formal charge. The difference, again, I'm going to say it again because it's important. Formal charge, we assume everything is equally shared. When we're calculating oxidation state, we assume that the most electronegative atom in the bond gets all of the electrons. Okay? So, when you're looking at something like ethanol, CH3, CHHOH, if we wanted to know the oxidation state of that carbon, we can calculate it pretty easily. We know that carbon comes in with how many valence electrons? 4. Now I've got to subtract the assigned electrons, right? So I've got to look at the electronegativities. Okay? I know that the electrons in that carbon-oxygen bond are all going to belong to oxygen. These two are going to belong to oxygen. Okay? Oxygen is more electronegative than carbon. Okay? So I'm not going to assign those electrons to that carbon. Okay? I know that carbon is more electronegative than hydrogen by a little bit. So I'm going to assign all of those electrons to carbon. What about a carbon-carbon bond?
Just one.
Equal.
It's equal, so I'm going to just give it 1 electron, right? So I'm not going to give it any of those. I'm going to give it 2, 4, 5. 4 minus 5 is what?
Negative.
That's right. That oxidation state for that carbon is -1. What about if I had, let's say, CH3, C double bond O, H, and I wanted to know the oxidation state of that carbon? Again, carbon comes in with how many?
4.
4. And now I'm going to subtract the number formally assigned to it. Does it get any of these from the oxygen?
Not at all.
Not at all. How many of these does it get?
2.
How many of those does it get?
1.
So it's 4 minus.
3.
1.
This is in the +1 oxidation state. This one is in the -1 oxidation state. The more positive you become, the more oxidized you are.
Why does it not get any from oxygen? I can't remember why.
Because oxygen is more electronegative than
More
carbon.
electronegative.
Yeah, it's all about electronegativity. Now let's look at one of the most highly oxidized forms of carbon. Everything that you're breathing out right now. Carbon dioxide. What's the oxygen state? What is the oxidation state of that carbon atom? It comes in with 4. How many does it formally own now? 0.
-4?
Well, +4.
Oh, sorry.
That's fine, yeah. +4. What you will find is that we've got -1, we've got +1, we've got +4. What if we did methane?
-4.
4 minus how many? 8? It gets all of them, right? Because carbon's more electronegative. What you will find is that carbon can have oxidation states that can go all the way from -4 to +4. It's one of the beauties of carbon. It sits on a very special place in the periodic table. I've told you that before. It's why we're carbon-based and not silicon-based. Okay? Because carbon can actually do all of these oxidation states. Okay? And so, what is the difference between ethanol and acetaldehyde that I've shown here? Both of them have 2 carbons. Both of them have 1 oxygen. What's the difference?
Less hydrogen.
Less hydrogen, right? So it went from a more reduced state to a more oxidized state. And it's easy to see. I've got more bonds to oxygen. That should be more oxidized, right?
Yeah.
That makes sense, right? So you got to know how to calculate these oxidation states. There will be a question on the exam about calculating an oxidation state. I'm going to give you that one, okay? I'm going to put a molecule up there. I'm going to point to a carbon, and I'm going to say calculate the oxidation state of that carbon, okay? And I'm not going to make it complicated. I'm just going to ask you to do a little bit of that, okay? Now, on your own, calculate the oxidation state for the 2 carbons that are shown here. So the carbon in methanol and the carbon in formic acid. What's the oxidation states of those carbons? You do your own calculation. First thing I write down is the number of valence electrons for the atom that I'm looking at. It's carbon, it's 4. How many does it own?
6.
It owns 3 bonds, but how many electrons are in 3 bonds? 6. Right? So methanol's carbon is in the -2 oxidation state. Right? Formic acid. Again, carbon comes in with 4. We subtract how many it owns. How many does it own?
2.
It is in the +2 oxidation state. Anybody know where they come into contact with formic acid before? How many people in here have ever been bit by a fire ant? You've been injected with formic acid. That's the sting. Okay?
So,
Those little buggers make that stuff.
where do you get this 6 and 2 from?
The 6? All right, so oxygen gets these electrons. Will you agree? Because oxygen's more electronegative. So just erase it. 2, 4, 6. Because there's 2 electrons in a pair. So 4 minus 6 is 2. Minus 2.
Okay.
Here, the carbon doesn't get those electrons. It only gets these 2. So 4 minus 2.
Okay.
Does that make sense? Good deal. We can oxidize alcohols pretty easily. It's one of the things that we will actually let undergraduates do in my lab with no problem. The reactions never fail. I should say that. They rarely fail. They're very well behaved. We've got reagents that do these oxidations very well. You all might be familiar with the oxidation of alcohols if you've ever opened an old bottle of wine that went to vinegar. You've probably heard that term before, right? The wine is spoiled, it's gone to vinegar, right? Think about it. The alcohol in wine is ethanol, and that can go to vinegar, which is CH3, C double bond O, OH. All you got to do is oxidize ethanol, and you can get vinegar, acetic acid. It happens. If you leave alcohols out for a long period of time in air, they will slowly oxidize. That's why they put tight corks in wine bottles. That's why you're supposed to store them a certain way, yada, 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 yada. You're supposed to drink them not long after you open them up, all that kind of stuff, because the ethanol will oxidize. It's a pretty slow process. It's not going to happen while you're drinking your glass of wine. It's not going to happen over the next few days or anything like that. But we can speed the reaction up by using certain reagents that actually do this. So, I need to show you some shorthand here. Anytime you see a bracket with an O in it like that, that means oxidation. I'm not telling you at this point what we're using to do the oxidation. I'm just telling you that we can take a primary alcohol and we can oxidize it either to an aldehyde or a carboxylic acid. Primary alcohols can be oxidized to either aldehydes or carboxylic acids. That needs to roll off your memory. A primary alcohol can be oxidized to an aldehyde or a carboxylic acid. It depends on what the species we're using to do the oxidation is, and we'll talk about that. Okay? Secondary alcohols. Oh, I keep thinking I've got my plugged in. I don't. Secondary alcohols can only be oxidized to ketones. That's easy to remember. If I've got a secondary alcohol, I've only got one carbon-hydrogen bond to oxidize. So I'm going to get a ketone. A primary alcohol, I've got 2 carbon-hydrogen bonds, so I can get 2 different products. What do you think is going to happen with tertiary alcohols?
Won't happen.
Yeah. No reaction occurs. Why does no reaction occur? Because there's no hydrogens attached to that carbon. I can take a tertiary alcohol and I can leave it out in the air, and as long as it doesn't evaporate, I can come back in 100 years and it's still going to be a tertiary alcohol. But if I went to an estate sale that had one of Thomas Jefferson's original bottles of wine he had, I wouldn't want to drink it. I'd only buy it because it was owned by Thomas Jefferson. It would be vinegar inside. It would have had a couple hundred years to oxidize, and it would happen, and it would taste like nasty vinegar. Okay? So people pay millions of dollars for these bottles of wine that you can't drink just because of who owned them. Yada, yada, yada. Okay? So, primary alcohols can be oxidized to what? Aldehydes or carboxylic acids. Don't say and or. It depends on the reaction condition. Secondary, give me? That's all you got to remember. Tertiary alcohols don't oxidize, and there's no such thing as quaternary alcohol. You can't have 5 bonds to carbon, right? The trick is going to be knowing what's going on with these primary alcohols. Because you know, no matter what reagent we use, if it's an oxidizing reagent, a secondary alcohol is always going to give me a ketone. Okay? Whoop. Okay? Well, it turns out that chromium on the periodic table is a pretty good oxidant. Okay? I actually accidentally did this experiment one time where I oxidized an organic molecule, which was an alcohol, with chromium, and it really caught on fire. I mean, it was oxidizing very, very quickly. Chromium is in the +6 oxidation state. It wants electrons. Right? Think about it. Chromium surrounded by all these oxygens. These oxygens are pulling all the electrons to themselves. Chromium wants some electrons from somewhere. Where's it going to get them? It's going to get them from those CH bonds. Okay, that's where it's going to steal them from. Okay, and so you can have a reagent that has chromium trioxide in it, CrO3, and that will oxidize primary alcohols. It will oxidize secondary alcohols. So you need to know this list up here. So you can use chromium trioxide, which is the one that I like, which you'll probably see on the exam. But you can also use a molecule known as sodium or potassium dichromate. These will also do the same thing as chromium trioxide. In all cases, chromium has a very high +6 oxidation state. These are strong oxidants, and that you usually make these up in a solution of sulfuric acid and water. Okay?
What are these used for again?
Oxidation.
So we use, so this is what that O was in the brackets?
Yep, this could be your O. Yep,
Okay.
any one of these. Okay? So, if you came up to my lab, we actually have a bottle of this, but we've called it Jones reagent. So a solution of sulfuric acid, water, and chromium trioxide is known as Jones reagent, and it will oxidize alcohols. You can also have this compound here that we call PCC, stands for pyridinium chlorochromate. And it too has chromium in the +6 oxidation state. The difference is this is not soluble in organic material, it's only soluble in water. This is soluble in organic solvents, so I can put it in things like dichloromethane, whatever. Okay? It's a little bit milder of an oxidant because there's no water around. Okay? But you don't need to worry about that just yet. We'll get to that. So, I'm going to hold you responsible for these chromium reagents. So keep, these would be good things to have in your notes. Okay? Now, why do I need 2 or 3 flavors of chromium reagents? Well, here's why. Again, remember, primary alcohols can oxidize to give you either what?
Aldehydes or carboxylic.
Aldehydes or carboxylic acids. If I take a primary alcohol and I react it with PCC, it will stop at the aldehyde stage. So if I want to convert an alcohol into a aldehyde, I'm going to use PCC, and I will get this aldehyde. This is what your liver does. But your liver doesn't have any chromium in it. Chromium is extremely toxic to humans. You have an enzyme. You'll probably learn about it in biochem. Okay? Cytochrome P450 is a strong oxidizing enzyme. Your liver takes ethanol. This isn't ethanol. But your liver takes a primary alcohol and oxidizes it to acetaldehyde, which is why you get a hangover. It's toxic. Okay? And you end up with the aldehyde. If I use one of the other chromium reagents, like chromium trioxide or one of those salts, here I'm just showing one of the potassium dichromate salts, notice there's sulfuric acid and water around, what product do I get? I get the carboxylic acid. It will oxidize it all the way to the carboxylic acid. Now, if I take a secondary alcohol and I react it with PCC, I get a ketone. If I take a secondary alcohol and I react it with Jones reagent, I get a ketone. It's the primary alcohols that you have to pay attention to. Okay? So keep that in mind.
So we only get aldehydes when we use PCC
And a primary alcohol.
and a primary.
Primary alcohol and PCC will give you an aldehyde.
So if it's primary and not PCC, then it's carboxylic acid.
Yes. Yes, you are right. Now, it turns out that chromium since it's an oxidant, what happens to the chromium? If something is an oxidant, that means it gets reduced. Okay? So chromium is taking the electrons from the alcohol to reduce itself, right? And it turns out that these chromium reagents have different colors depending on their oxidation state. Chromium in the +6 oxidation state is kind of an orange color. Chromium in the 3+ oxidation state, which is more reduced, is actually green. And so they used to make these little things for people to test their alcohol content before they would get in the car. So back in the 80s, when there was Mothers Against Driving Drunk, MAD, whatever they called it, they would go to these teenage parties. I remember going to them when I was a kid, and the mothers would hand out these alcohol test kits. And before you got in your car, you were supposed to blow into this. There was a bag at the end of it, I think, if I remember right. And you would measure the color change. Well, the tube contains the chromium reagent, which starts out as being orange. And as you blow into it, it gets reduced if there's alcohol on your breath. And the further that green moves, the drunker you are, okay? The more alcohol is in your breath. And so if it made it to a certain point, you were inebriated and you weren't supposed to drive, okay? As you can imagine, we don't really use these too much anymore because chromium ended up being in the trash. Chromium is actually a very bad for the environment. So now they have electronic devices that you can breathe into that measure your alcohol content. But these were the way that they did it back in the old days. They just used color changes, okay? And so there's a picture of what used to be called the breath scan, and you can see it's kind of a yellowish orange color there, and then you would measure how far the green color moved, determine whether or not you could drive or not. This is what I've done in the lab. I've taken a little better picture for you. So I took 2 Petri dishes, and I put chromium trioxide and sulfuric acid. This is Jones reagent without alcohol. I think you all will agree that's orange, right? And then I took some absolute ethyl alcohol that I had in the lab, and I put a few drops in this Jones in another vial of this Jones reagent, and look at the color. It's green, right? So I took ethyl alcohol, I dripped it into Jones reagent. What was the product that I got? The organic product.
So what degree of cells?
It's ethyl alcohol.
Ethyl?
Uh-huh. Just pure old ethyl alcohol, good old Everclear there in the bottom.
Carboxylic acid.
Yeah, I ended up with vinegar. Ended up with acetic acid, right? So ethanol reacted to give acetic acid when I used the chromium trioxide. But it changes the chromium into the +3 oxidation state, which happens to be green. The nice thing about these reactions when I have an undergraduate student coming in to do research and we have to do one of these oxidations, is you just drip in the Jones reagent until it turns completely green and you're done. It's just that easy. The color tells you that the reaction is over, and that's kind of nice and neat and convenient. Oop, pushing the wrong thing. So that's what's happening. I'm taking ethanol and I'm converting it to acetic acid. Okay. Now, like I mentioned, in your body, you have enzymes that do this, okay? So when you ingest ethanol, your liver oxidizes that first to acetaldehyde. So if you drink a lot of ethanol really, really quickly, you get that fuzzy feeling. That is your body dying, okay? You are generating acetaldehyde. That acetaldehyde is toxic. Your liver hasn't been able to completely process that yet, okay? But your liver will take acetaldehyde and actually oxidize it further to the carboxylic acid. So your liver has the ability to do essentially what chromium trioxide can do. But if you drink too quick, you build up too much of this and it can't process it to this fast enough. This ends up in the blood. It dehydrates you. It makes you feel funny. It gives you what is the characteristic hangover feeling, okay? That's acetaldehyde. You have an enzyme, okay? There's several enzymes. There's cytochrome P450, which I mentioned, but there's one called alcohol dehydrogenase as well that will take alcohol and convert it into the the aldehyde and the carboxylic acid, okay? You've probably heard about not drinking methanol. It's toxic. Methanol itself is not toxic. The products of its oxidation are toxic. So methanol gets oxidized by alcohol dehydrogenase, just like ethanol does, but it makes formaldehyde as the aldehyde. What do you all know about formaldehyde? You use it to preserve tissue. What is preserved tissue? Is it live or dead? It's dead. Okay? Formaldehyde will pickle you. Okay? It will then ultimately get oxidized to formic acid. Formic acid will also increase the pH level of your blood and kill you. So you get two things out of this process that kill you, okay? And really, I think you only have to drink about 10 milliliters of methanol to go blind, and you only have to drink about 100 milliliters of methanol to die. So this is why if you go out and you get illicit alcohol from somebody who's a distiller, please make sure they know what they're doing, because if they gave you the Forerunner or the Heads, it's full of methanol, okay? And you want to avoid that. So never take that first run of a distilled spirit and drink it, because it's going to contain a lot of methanol. You want the ethyl alcohol. All right. So we are going to cover up through the oxidation of alcohols for the exam. We are not going to talk about ethers per se. That means what I'm going to say is none of the reactions of ethers will be on this exam. Okay? But we have talked about ethers a little bit, right? We talked about crown ethers. We talked about being able to make ethers from SN2 reactions. Those would be fair game. But we're not talking about the stuff in the second half of the chapter at this point for the exam. Okay?
So is that until 8.3?
Yeah, it's about 8.3. Yep, we're at about 8.3 right now. So remember tonight at 5:30, if you all want another help session, I'm going to be upstairs in 411. I'm not going to record tonight's. I recorded yesterday's. I got that up there, but I won't record tonight's. It'll be about the same. If you want to come tonight, that's fine. The exam, again, is going to be 25 questions. You're going to have a zip grade. You're going to have the periodic table. You're allowed a simple calculator. For those of you who haven't watched the video from yesterday, what is a simple calculator? Can't connect to the internet. It could be scientific, but it can't connect to the internet. It cannot be your phone. It cannot be your smartwatch. Okay? Why would you need a calculator? Number one, you're going to be doing some oxidation state stuff. I think you can do that without a calculator, but if you need it, you've got it. And then specific rotation, right? So that kind of stuff you might need a calculator for. Okay? I will not be here Wednesday. My wife will be administering the exam for me, so I will not have your results of your exam back before the first part of next week. So I apologize for that, but good luck, and I will see you all later.